Calculus lesson on related rates. Okay, guys, take a note here, please. Oh, by the way, please write your name and the date when I check your work. Okay, when you submit your work. Okay, appreciate that. All right. So 3.9 related rates. What exactly is it? Yeah, I'm gonna use a lot of repetitive word, but here it goes. Uh, Basically, related rate problem involves finding a rate at which the quantities change by relating it to another quantity, like for example, y with respect to x, right? But we're not differentiating them. We want to know over time, let's say dt, how does that relate to dy dt, right? So we want to know how the two different variables are related that way, right? Well, anyways, so here we go. The first step is to draw a picture. Number two, we want to write a general equation that relates the two, three, multiple different variables, and they will differentiate implicitly, meaning that you don't have to solve for the y or the x or whatnot, just differentiate as it is, right? And then we'll find the qualities from the givens, right? From the needed qualities from the givens. So for example, so this is a given information. This 20-foot ladder is against the wall. The bottom is sliding out. So we're gonna have to kind of graph this out first, right? So that's L right there, guys. That L is 20. And that's sliding out this way at 2 feet per second. Let's call that X. Then that is dx dt, isn't it? And let's call that Y. Oh my gosh, X squared plus Y squared is 20. We have an equation right here. And if that's the case, when is it when the height, the wall is equal to 12? But what is that equal to? So we have to find all that information. And then ultimately, using the equation that we had over here, find dy dt. Is that right? Exactly. Why don't you guys pause the video? It's always a good idea to pause the video and try this on your own if you feel very confident. If not, just wait a couple of seconds. All right, guys, I want to assume that you tried this on your own already. And here it goes. Let me just start with a picture first, right? So you draw a picture. It's pretty much the picture that I kind of laid out for you earlier, but this is the given information 12, and that is 20, right? So I drew that picture right here, 12, 20. But what do they have in common? 4, right? It would be 3 and a 5. At a right triangle, that has to be 4. Because it has a scale factor of 4, 4 times 4 gives you 16. Remember that from geometry? Exactly, right? And then I write the much needed information dx dt is 2 feet per second. And right here, I want to know what my dy dt is equal to. Okie dokie. Sliding all the way across, noting the relationship of the x, y, and L, right? This is what we have. We take the derivative. There you go. But you know that that's constant, right? So simplifying the expressions, instead of solving for dy dt, I decided to just plug the values in there, right? When I did, 16, y at that length is 12, and dx dt is 12. I solve for that, I move that to the other side, and I don't multiply it up because it will be easier for me to cross cancel. And from negative 16 over 6, I could quickly see that's negative 8 thirds feet per second. And it's a good form to respond in a complete sentence. Okay. So the top of the ladder is sliding down at negative 8 third feet per second when the bottom of the ladder is sliding out at the rate of 2 feet per second. Okay, good. So we got two more questions. You might want to pause the video if you don't want my help and if you don't try this on your own. Okay. All right, guys. Here comes the hint. Here, you want to draw this thing, cone, like that. Height is 12, the base is 6. And then something's being pumped in, right? dVdt at 10 gallons per minute. How fast is it rising? Okay, so there's a water already. So that's height. And that's the radius. And the height is equal to 3. And you know that height's on the right, dH dt. That's what we're looking for. So we're going to relate the volume. It's a cone. Oh, cone is 1/3 pi r squared h, isn't it? Yeah, we're done. And clearly we're going to have to do some unit conversion, or the chemistry teachers like to call that dimensional analysis, right? Right. Okay, how about this one? Hint. A camera is 3,000 feet from the rocket launch. So something's going up this way. That distance here is fixed. That's 3,000. And that's the y value. Or we could just use h, right? And then how fast the theta. So we're asking for how d theta dt is changing, right? Because y is increasing. But it's increasing at what? dy dt at 880 feet per second. Well, how do you connect the length, the adjacent, and the opposite? It's tangent theta is y over 3,000. There you go, guys. That was it. All right, guys. Pause the video. Okay, I'm back. So initially, I started with step number 1. I drew a picture. This is 12. This is 6. Just remember that the radius is 3. So the height over here is 4 times radius. Oh my gosh. Is that the equation that we're going to be using? Apparently. At least that's the constraint, right? Between the two variables. And then we're given that the height is 3 of the water, and that's the radius over here, guys, right? We're looking for the HDT, but given information is that the VDT, the volume is increasing. That's a plus at 10 gallons per minute. Step number 2, we need to know the volume versus the radius versus the height. So what do we do afterwards? We differentiate them right here. It's already done. So now we have to plug in some information, right? So before we do though, these were given information that was already here. But how do I find this value over there? So here it is. If that's 3, that's 12. This triangle is height to radius is 12 over 3. And which gives you height is equal to 4 times the radius. If you differentiate that, dh dt is equal to 4 times dr dt. Right? Right. And then if the radius is equal to, if the height is equal to 3, that is 4 times the radius, solving for the radius is 3/4. So when height is 3, the radius is 3/4. And we found out that dh dt is 4 times dr dt. So we plug in all that information, guys, right? From here. And then dvdt is 10 gallons, but we need to convert that into feet per second. So that we do the conversion factor right there that was given to us, right? Anyways, so we plug in a whole bunch of values here, right? And we factor out the DHDT. Bunch of work was done. I didn't want to bore you with that. And then we ultimately came to this, which is about 0.757 or 0.7566 feet. It increases by that feet per minute. Okie dokie. All right. All right. So if you still have a question on it, we could go through this in fine detail in class, right? And look at this. Camera, 3,000 feet from the, I drew this picture for you already, right? And I wrote all the pertinent information over here. And the height at that point that we want to calculate is 4,000. So the equation that we have is tangent theta is y over x. And at that point, x is 3,000. Well, actually, x is always fixed. That doesn't change. So that's the equation right here, guys. So we do implicit differentiation, which gives us secant squared theta times d theta dt is 1 over 3,000 times dy dt. At this point, using this information over here, guys, right, we know that the tangent of theta is 4/3. If that's the theta over here, what is secant theta equal to? Why do I want to know secant? Because I have secant over here. That's why. right? And then we know the secant theta is obviously 5/3. And plugging that information over here, we know that dy dt is 880. Plugging that information, solving for that, I get 66 over 625 radians per second. Okay, so the camera angle is changing 66 over 625 radians per second when the rocket is 4,000 feet above the launch pad. Nice. Okay, guys, this will be your turn. I didn't mark it, but this is your turn. Very important. Walking away. What is that? What if it's walking towards? How does that change things, right? Okay. And then it's talk about shadow length. Draw the picture. Which is the shadow, right? And it's talking about the tip of the shadow. How's that different? You'll be able to see when you draw the picture. Okay, guys? All right. The second question that you have is this. Okay. All right, guys. Why don't you work on this one? And then you should compare this with your classmates when the class begins next class. All right, guys? All right, that is it. And then I'll talk to you in class. Okay, bye-bye.